For 2,000 years, humanity calculated pi using the most painfully slow method imaginable. Generation after generation, the smartest mathematicians on Earth repeated the exact same exhausting physical process just to try and understand the circle. The trap they were stuck in seems simple. The area of a circle with a radius of 1 is exactly pi. If you can calculate that area, you know the number. But a circle is a continuous curve, and before the 17th century, there was no way to perfectly measure a curve using straight lines. This was the ancient world's workaround, developed by Archimedes. Because he couldn't measure the curve directly, he approximated it by trapping the circle. He placed a hexagon entirely inside the circle and wrapped another hexagon around the outside. Since a hexagon is just 6 straight-edged triangles, he could calculate those areas perfectly, pinning pi somewhere between the two. To get closer to the true area, you double the sides. 6 sides become 12, then 24, 48, and 96. With each step, the polygons squeeze the circle tighter. But every single time you double the sides, you have to extract nested square roots by hand, over and over again. To find a precise numerical value, you were forced to calculate the dimensions of an agonizingly complex physical drawing. For 2 millennia, humanity remained stuck in this geometric bottleneck. This bottleneck demanded an extreme human toll. In the 5th century, the Chinese mathematician Zhu Chongzhi pushed this method as far as it could go. Using thousands of wooden counting rods laid out on a board, he tracked the perimeters of a polygon with over 24,000 sides. All that labor resulted in just 7 decimal places of accuracy. 1,000 years later, the Dutch mathematician Ludolf von Salen went even further. He spent 25 years of his life grinding through the arithmetic for polygons with more than 4 quintillion sides. A quarter of a century of work secured him exactly 35 correct decimal places. This graph illustrates the wall they hit. In mathematics, this is known as linear convergence. For every single new digit of pi you want to discover, the process demands exponentially more manual arithmetic than the step before it, while yielding smaller and smaller returns. The polygon method itself hadn't failed. The human mind had simply reached the absolute physical limit of calculating shapes by hand. Then, in 1665, the Great Plague forced Cambridge University to shut down. A 22-year-old Isaac Newton retreated to his family farm, placed in strict isolation with nothing to do but think. Newton wasn't trying to break any records. He was focused on a much broader problem: building a universal machine that could calculate the area under any curve. While reviewing current formulas, Newton realized that by taking the binomial theorem, a tool for expanding expressions, and applying fractional exponents, he could bypass the need to draw physical shapes entirely. The equation for the top of a circle is the square root of 1 minus x squared. Newton forced this continuous curve to break apart. It dissolves into a sequence of simple fractions. Geometry had been translated into analysis, expressed as pure arithmetic that never ends. An infinite series is only useful if it hones in on the answer quickly. If the math takes a billion steps to get close, it's no better than a polygon. To solve this, Newton used a strategic shortcut to accelerate the arithmetic. Newton used a circle with radius 1/2, isolating the interval 0 to 1/4 to create a 30, 60, 90 triangle. Replacing x with 1/4, each step multiplies by its powers, a 16th, a 64th. The sequence shrinks exponentially, instantly locking in pi. By merging the geometry of that triangle with the mechanics of his series, Newton had engineered a way to calculate the area using simple, repetitive arithmetic that moved faster than any previous method. The efficiency of this method was unlike anything that came before it. Using just 22 terms of this sequence, Newton calculated 15 decimal places of pi. What cost Ludolf 25 years, what took Archimedes months of labor, Newton did in one afternoon. The 2,000-year bottleneck was shattered. Humanity no longer needed to draw a polygon to understand a curve. Years later, Newton wrote a letter to the Secretary of the Royal Society about these calculations. He admitted he was ashamed to tell them how many digits he had carried the math to, having nothing else to do at the time. He was embarrassed because the digits of pi were just a byproduct. To Newton, they were the exhaust fumes of a much more ambitious machine. Newton hadn't just found a faster way to calculate a constant. He proved that his new method of flexions, what we now call calculus, could convert the geometry of the physical world into a stream of predictable data. In solving the circle, he provided the ultimate stress test for the math that defines our modern world.